Engineering College, Katpadi, in the EEE department. I take this opportunity and the privilege on behalf of Ranipet Local Center to welcome you all for this lecture session. I would like to introduce Dr. Deepa. Dr. Deepa Sundaresan received her BE degree in IRTT E-Road in the year 2000, and she has completed her ME degree in Anna University campus in 2007, and she has acquired her Ph.D. degree with a UGC fellowship in electrical engineering from same Anna University campus under the guidance of Dr. P. Vanaja Ranjan, Professor Embedded System Technologies, Department of EEE, and the Director, Center for Faculty Development, Anna University. She is currently a professor with Electrical and Electronics Engineering, Kingston Engineering College, Katpadi. She has teaching and research experience of about 21 years and authored or co-authored 11 papers in reputed journals and 7 international conference papers. Her current research interests include signal processing, fault diagnosis in electrical machines, power quality, and embedded systems. She is a recognized supervisor in Center for Research, Anna University, guiding 5 scholars in part-time. She is a convener of Institution Innovation Council of Kingston Engineering College and organizes many events on innovation, intellectual property rights, and entrepreneurship. Coordinator of Smart India Hackathon, Professor Deepa is a lifetime member of the Institution of Engineers India, organized in Anna University Center for Faculty Development. Sponsored faculty development program on digital signal processing from 11/7/22 to 16/7/22 with eminent personalities from reputed institutions and industry. With this small introduction, I request Dr. Deepa to handle this session. Thank you, madam.
Yes, sir. Thank you, sir. Thank you for the introduction and the support, sir. Saleh Manalan, sir, has supported me in all the endeavors. Whenever I ask him, he'll be supporting me. Thank you, sir. Thank you so much.
Thank you, madam.
So here, my presentation will be on fault diagnosis in electrical systems using signal processing techniques. This is my research topic, and I had done this under my supervisor, Dr. P. Vanaja Ranjan. I thank my teachers and my well-wishers for the development and the help they had showed to me to stand in this position. Thank you. So here it is, the digital signal processing is the main part of the control in all the electrical process controlling instrumentations and everything. And we'll be seeing, I had taken up basic work of how the signal processing technique is used in electrical fault diagnosis. I'll proceed with the presentation. Yes. 1 minute. Okay. So here it is. What is condition monitoring? So our human body is also a great architecture of God, and here whatever any difficulties in the system will be reflected in terms of temperature increase, or any difficulty in the system will be indicated. So as in the machine also, it will be having, if any difficulty, there is some stator fault or rotor fault or eccentricity, it will be showing in some vibrations, increase in the temperature, likewise. So that is that is the main definition. We'll go for condition monitoring technique. What is the definition is? Condition monitoring can be defined as technique or a process of monitoring the operating characteristics of machine in such a way that changes and the trends of monitored characteristics can be used to predict the need for maintenance before serious deterioration or breakdown occurs, and or to estimate the machine's health. So we can estimate what is the what is the age of the machine can also be detected. So how much, what is the, by monitoring the parameters. So we are measuring the temperature of the body. So in the same wise, we can see different parameters of voltage, current. So whatever there is a disturbance in the machine will be reflected in the input side. Okay, so in the anywhere we'll be having the supply, we'll be having the drive, variable speed drives, we have the motor and the load. So wherever the fault is, we have to detect either the fault in the load or in the machine or in the drive or in the supply. That has to be detected. Okay, without keeping hand on the system. So automatic detection. That is the main. Why we have to take up this condition monitoring. So industries, they'll be monitoring the n number of machines will be there in the now you can use this technique can be used to detect the fault very easily. Okay, so here it is reduce the maintenance cost, it lengthening equipment's life, enhancing safety of operators, minimizing accident, severity of destruction, improving the power quality. So basically 3-phase induction motors are going to be used in industries. They are the most rugged and there will not be any much problems. So if we are going to, it is the inductive load. So whenever there is a inductive load, you will be having some harmonics and all induced in the power supply. So it is getting polluted. So that harmonic has to be reduced. So that is the main cause. So what is the current? Here is ideal condition monitoring technique and current monitoring technique. So here we are going to use the current as the basic parameter to signature the machine fault. Okay, so here you need the sensors, non-invasivity, sensor and instrumentation, systems reliability, diagnosis reliability, fault severity, quantification. So the first 4 steps comes under the current monitoring technique. The next is the remaining lifetime estimation, cause of the fault prediction. So all these 6 steps will come under the ideal condition monitoring technique. So what are the recent challenges in the research in this field? So here it is, the reliable identification and isolation of faults are still, however, under investigation as there are some open issues. So if we need by seeing the pulse, you can detect what type of disease or something, what is the condition of the human body. So there should be a single diagnostic procedure for identification and isolation of any type of fault. So reliable fault detection for position, speed, torque, and controlled drive in time varying conditions. So you will have different loads at different times, different speed. Okay, so reliable fault detection for position, speed, torque, controlled drives in time varying condition. Quantitative fault detection in order to state an absolute fault threshold independent of operating conditions. So we need a quantitative fault detection in order to state an absolute fault threshold independent of operating conditions. Need for including intelligence in machine diagnostic systems. So we need a intelligence, or nowadays machine learning techniques are used for diagnosing the machine faults. Need for incorporating faster retrieval of fault event for further action. Okay, so here the process of any industry should not be stopped. So we should be in a very varumun kapadenalam. So that is the process that we take up in all the industry or in the any life events. So here we have the literature. So what are the papers that they are discussed about this one? Focus on research, condition monitoring of electrical equipments. So electrical equipments means we'll consider both nowadays special machines are also coming inside, and then you have induction motors, transformers, everything is a electrical equipment. Stator winding, our power grid is also a network. So there also you can have different equipments embedded in it. Stator winding fault diagnosis. So first we consider about the motor. So stator, rotor, bearing fault, gear fault. So what are the fault diagnosis, distribution transformers? So fault diagnosis in variable speed drives, smart monitoring of machine health diagnosis, power quality event detection. So these are the topics that I'll be touching upon. Basically, what here is, what are the sources of machine fault? You will be having the internal and the external faults, the mechanical and the electrical fault. In the internal, we'll classify. So what are the causes are moving coil movement. Coil வந்து நகர்ந்திருக்கும். So bearing faults, rotor strikes and eccentricity. What is the electrical fault is dielectric failure, rotor bar crack, magnetic circuit faults. In the external one, you'll be having about the electrical environment and mechanical fault. You'll be having in electrical the transient voltage fluctuation, unbalanced voltage. So in the environment means you have humidity, temperature, and the cleanliness. Mechanical is pulsating load, poor mounting, overload. So these are the types of fault that can occur in the sources of machine faults. Next is the transformer. The main components that ensure the normal operation of transformer is the core, main tank, cooler, and the oil. What are the on-load tap changer? So they'll not change the taps because often tap changing will cause to the joints will get heated up and there will be some disconnections. Because of that, there will be some fault. So it's an on-load tap changer. Winding, that is a frequent failures that will occur. Aging of the oil or paper insulation in both winding and main transformers. So these are the types of faults that will occur. So in the literature survey, we see among the industrial motors, three-phase induction motors are dominant because of their simple design, rugged performance, easy maintenance. It is estimated that about 69% of induction motor failures are caused by bearing failures, and 21% by stator winding faults, 7 by rotor fault, and 3 by shaft coupling. Okay, so these are the different types of fault and what the literature says. So what is the objective of the research? Detection of faults in electrical machines like three-phase squirrel cage induction machine, variable speed drives, and distribution transformers using various signal processing techniques. Next is the wireless communication of fault type occurring in the equipment to a control module through ATmega 3 to 8 processor with global system for mobile communication. That is the GSM module. So it is to communicate wirelessly. Nowadays we have the we'll see it what it is next. So what are the signal processing techniques used in this thesis are going to be the root mean square one. That is the you can classify the signal processing techniques into two types. One is the time domain and the frequency domain type. In the time domain type, we have the RMS, that is the root mean square value. Quadratic mean is a statistical measure of the signal's magnitude. Crest factor, that is the ratio of peak value to RMS value. Power spectral density, that is the mean square spectrum periodogram. It is the FFT of an autocorrelated signal with a rectangular window. So there are different windowing techniques available. I use the rectangular window here. So spectrogram or short-term Fourier transform, that is STFT. Time and frequency resolutions depend on the size of the window. So this is also one type of, now we'll have the frequency domain. In the frequency domain, you'll have two types. One is the quadratic and the non-quadratic. In the signals, in this STFT, this wavelet, they come under this type, quadratic type, and non-quadratic type, we have the other things. Okay, so here I use the quadratic type. The basic functions are what is the discrete wavelet transform. The basis functions are formed by shifting and scaling of the mother wavelet in time. Discrete wavelet packet transform, both approximation and detail are considered. Wavelets are mostly used in image processing, 1D and 2D. As signal is going to be the one-dimensional one, and we have our images two-dimensional, and the video will come under the three-dimensional one. For all this, we can apply the wavelets. Next is the substral analysis. Substral analysis, while we are analyzing this audio signals, we got this method, substral analysis. There is a spectrum of a spectrum. It is a measure of rate of change in the different spectrum bands. And we have the adaptive peak filters, estimates harmonic signals, its amplitude, frequency, and the phase. So here, different signal processing techniques are used in my thesis. Next, what are the types of fault that I focus here is, here we have the stator winding fault. In the stator winding fault, we can consider turn-to-turn fault. You know, we would have seen the motor, the coil and all. So a single turn-to-turn, one turn open in a phase to phase, single phasing, phase to neutral, coil to coil. So there are different types of fault in the stator winding. Rotor fault, rotor bar broken, crack in the rotor. So rotor is a very rare fault. And bearing fault, this is the dominant fault in the machines. Healthy ball fault and inner and outer race. Gear fault, you have healthy and the notch tooth. So all these type of fault, we simulated the fault. So in the literature, they'll say that is if this type of fault is there, these types of frequency will shoot up. Okay, so normally our supply frequency is 50 hertz. You will be harmonics is the one which is the multiple of the integer of the fundamental. So it will be of mostly hard harmonics will be shooting up. Even harmonics will not be there. So here it is the Fs is the state of F. This is the frequency components that are function of shorted turns in hertz. So whenever I have a stator fault, depending on these parameters, so F is the supply frequency that represents the fundamental in hertz, N is 1, 2, 3, sideband number respective to the particular harmonic. K is the 1, 2, 3 order or harmonic order. So you have, this is the sideband number. This is going to be your harmonic order, and P is the pole pairs. We have the slip S equal to Ns minus N divided by Ns. Ns is the synchronous speed of the motor in RPM, and N is the rotational speed of the motor in the RPM. Okay, so this is the specification of the motor. So we have to we have to generate a motor of that. We have to induce the faults. Okay, so that is the we have to simulate the faults. So we used to go for a repair shop. There we have the motors come for repair. We used to rewind it according to with the different tappings. They'll be helping us. Chennai Electrical Services, Mylapore. They helped me in all the and IIT Madras and Arunai Engineering Works, Ika Dangal, and IIT Suresh sir. Everyone joined the team and they helped me in this simulations and all. Okay. So here the specification of the three-phase squirrel cage induction motor taken for stator winding, fault emulation with mechanical loading is, we have this 415 volt, 1.5 kilowatt, 2 HP, 1430 RPM, 3.4 ampere, 36 slots, 1 coil per slot, 6 coils per phase, 54 turns in each coil. Total number of turns is 324. So we have to have a complete data of all the machines, what we work on. The tappings has been taken at different 1%, because short circuit means if we load, it should be done at no load condition only, shorting and all. Testing, if we load it and do the experiment, it will burn off. So 1% means third turn, 3% means 10th turn, 5% 16th turn, 10% 32nd turn in all the three phases. So this is the specification. This is the experimental test bed. This is the done at College of Engineering Guindy, electrical machines lab. So here we have the auto transformer. We have this current sensors. So we can tap it. So current sensors, they have 1000 ampere bar 1 volt or 100 ampere bar 1 volt. We can select the range of according to our applications. So this is the current sensors what we used. Here is the accelerometer to see the vibration of the machine, and here we have the audio measuring device. That is what is the sound of the machine. There we use the audio measurement system, and we have the this is also a current sensor of low rating. That is the anti-ampere bar 1 volt. Here we have the digital storage oscilloscope. So whatever this probe is connected to the oscilloscope, this is the data acquisition system. From the oscilloscope, we connect to the laptop. We have the software to track the data from the oscilloscope to the laptop, and then we'll take the data and we use for MATLAB wise simulation, or we can go for the online. Online means we can have the LabVIEW software for diagnosing the fault or calculating what are the frequencies that we have. So here, this is the table for different fault. What are the frequencies that is shooting up? So what we infer from that has been given. So this is the frequency spectrum for the, this one is the healthy motor. We have this one, you don't have that much thing. Whenever you have the short circuit fault, we can see different harmonic, interharmonic. Interharmonic is the one that is the that is the non-integer multiple of the fundamental is the interharmonics. Subharmonics are the one that will be less than the fundamental. That is the things. So you have harmonic, interharmonic, we have the subharmonic, and subharmonics are also there. And the high frequency machines are also, high speed machines are also used. There also, that is for so we have some machines for waste management, machines, so that come under a different category. So here we have the face-to-face fault. So by seeing the pattern, we can say what type of fault it is. So this, while paper publication, they'll be asking, so this much font, this much x-axis, y-axis, everything should be there, legends. So here we have the voltage and the, this is one type of fault. This is under load and no load condition of a 3-phase squirrel cage induction machine. So it is a one is open type of finding. Here we have 1 minute. Okay. So here we have the peak variation response of open circuit fault in stator winding. I saw one machine when one coil is also, one winding is also, sorry, one turn is open, we have to go for a rewinding of the machine. So here, this one, under no load and load condition of 3-phase machine, what will be the pattern? This is the, this is about, so whatever we had seen is for stator fault. Next is the balanced and unbalanced supply to 3-phase squirrel cage induction machine. So sometimes you would have seen voltage will come down, or sometimes it will show voltage will be high. So there will be some disturbance depending on the disturbance in the supply side, how the machine reacts. We have to study that. So here it is a auto transformer 3-phase. We have the input 450 volt 50 hertz and AC supply. So to give different voltages, I took 3 single-phase transformers in 3 phases, and then we have a 3-phase squirrel cage machine. This is the experimental setup. So we have the motor with the loading, and we have the turns, and we have the single-phase, the meters, multimeters for the voltage measurement. And we are studying the peaks, study on peak variation response for 3-phase squirrel cage induction motors applied with balanced input. Balanced input means in all the 3 phases, we will be having our, what to say, this one, voltage, frequency, phase, all should be the same. Unbalanced means the voltage will not be, voltage, frequency, and the phase, there will be some mismatches. That is called as unbalanced. Okay, so here you have the input or the stator voltage. And here you have the study of the patterns. We'll see the pattern that time we'll easily understand. So what happens here is to the magnitudes. What is that? We'll be studying the different magnitudes, and we'll be seeing it. So here it is with the some papers they'll be targeting only with the single fault. We used to target with multiple fault also. So stator mattum edupanga, rotor mattum, different signal processing technique vachu mudichiruvanga. So here we have a peak variation response for B phase under balanced supply, voltage input as 175 volt line to line in all the three phases. So here we have the different voltage. So what happens when the voltage is same and what with the stator fault? This one is going to be with the stator fault. So what happens when different supply has been given to the machine? So next, single phasing. Single phasing means one phase is not there and other two phases are there. So we can take the signals, plot it, we'll have the graphs and we'll see the patterns. So next is the rotor fault. So in the rotor fault also experimental test setup for rotor fault detection. Here we have the different, the rotor, the rating of the first motor with mechanical loading is 415 volt, 1.5 kilowatt or 2 HP. And so here the fault frequencies, when the fault occurs, what frequency will be there, the calculation formula. So this is the setup for rotor fault. And then we have the other machine we had. So in that, depending on the different study, there we had taken the mismatch in the magnetic field. Okay. So what happens if we have the strips on the motor? We had studied the analysis, and so different. There will be four. They would have cut the rotor and they would have inserted four other bars inside. So depending on the strips, how it reacts on the Mari. So what about the fault? So we'll see the different patterns and with the multiple fault, rotor and stator fault. So theoretical value and the practical value will be coinciding. So that was the beauty of the research. So whatever formula we get, we'll be doing. So comparison of all the different. So one rotor bar broken, no load, good rotor, no load, and rotor with 2 strips, no load, 4 strips, no load. So we'll study different patterns or signatures with and without load. So this is with the stator and the rotor fault. It's the multiple fault. So you'll have the frequencies for rotor as well as the stator fault occurring in the system we can find at no load and the half load condition. So next one, next is the bearing fault. In the bearing fault, this is the bearing. You have there are different types of bearing used in different locomotives. And here it is a ball bearing. In the ball bearing, we have the outer race. Here that's the inner race. You have the cage and this one is the balls. So the outer part will be stationary. The inner part will be a rotating one. So you'll have the diameter of the ball, diameter of the cage, and what is that angle beta. So whenever there is the inner and outer race fault, this formula, the frequencies of this formula will be there. So we have to know what are those things. Those formulas are there, and the bearing fault is given by magnitude of F plus or minus K into F car. So this is the formulas. So what are those things? So inner race, outer race, cage, and the ball. In the fault vandalum idha vechi kandupidichidalam. So experimental bearing fault diagnosis test bed. Here we have the supply, single phase supply. This is the single phase to 3-phase inverter, 3-phase induction motor. This is the plumber block 1 and 2. So over machine on the open panni bearing la maathradhu kashtam. So bearing mattum velila vechittu we will see the testing. So that is, this experimental is from IIT Madras. So here this is the experimental test bed. We have the motor, we have the coupling, and this is the plumbing block to support the bearing here. This is the cage where we have the bearing, and we have the load arrangement, hydraulic loading system, load cell, everything will be there. So this is the test bed. We got permission from head of the applied mechanics lab IIT Madras, and I had done this experiment there. So what is there itself, they had provided the bearings, good bearing, ball bearing, and inner and outer race fault and all. So this is applying your our crust factor, RMS, and was a slip taken under no load and load condition. Whenever we have different faults, that fault condition, the magnitude will be high. So that is the one thing. And then machine with healthy bearing, different types of bearing under load and no load. What is the pattern we have to study? And this is the overall table for the bearing. So there was some pattern which is occurring during the bearing fault for different fault. Here, this one is the one while I was doing the experiment in the shed, I forgot to fix the bolt in one side of the machine. So the machine start vibrating, and that time I took the rating, so readings and all. So it is a that is PVR is a PVR in spectrum of current for induction motor with mechanical asymmetry. Load side bolt of the motor is not fixed. Okay, so that one. So that is about the bearing. Now about the gears. So the gears are the one where we are using more speed variation, and the gear fault is going to be the somewhat Teimanam, and there are different types of faults in the gears. So let me see the current-based detection of faults in gears coupled to electric motors. A machine consists of power source and a power transmission system, which provides controlled application of the power. The transmission has been defined as assembly of parts, including speed changing gears and propeller shafts by which the power is transmitted from one engine to a live axle. Often transmission refers simply to the gearbox that uses gears and gear trains to provide speed and torque conversion from a rotating power source to another device. Spur gear. So what type of gear that I had taken as a spur gear? Teeth are perpendicular to the face of the gear, commonly available and less expensive. Cannot be used when a direction change between the two shafts is required. So this type of gear I had taken. So here we have the faults in gear trains. So what are the faults? So example, here is a railway traction system. We have in the wind energy, Leon gears. So these are the pitting, micro pitting, scuffing, root cracking, wear, scarring, and plastic deformation, case cracking. So in the Maria type of fault வந்து நமக்கு இருக்கும். So mechanical faults such as unexpected load torque, large torque dynamic variations, torsional oscillations lead to fatigue of the shaft driving electrical machines and other mechanical parts such as bearings and gearboxes. Example is a railway traction system. So this is about the gear. So what are the frequencies that will be coming for the mechanical fault is taken up here. So this is the rotational speed frequency of the shaft rotating, may be calculated as N is the gear ratio, P is the number of pole pairs. So this is the experimental block diagram, setup or a block diagram of the gearbox fault diagnosis test bed. So now we have the phase and the neutral supply, driving motor, gearbox driven motor and the load. Here we have the data acquisition used on the computer. So this is the setup. So this is the variable frequency drive VFD. We have the generator, DC generator. We have separately excited DC generator. We have the gearbox here. We have the motor. So here this is the resistive load setup, and we have for the separately field we have to give the excitation. That's why we use the transformer and the DC supply. This is the accelerometer. Here we have the data acquisition system and the laptop. Okay, so this is the this is also from IIT Madras Applied Mechanics Lab. So we have to see what are the equipments we used to go there. So half a day for setting up the experiment and this thing, and doing half a day the experiment, Sundays, Saturdays, or evenings, whenever we get the time, we used to go there. So single phase induction motor coupled to a gear and a separately excited DC generator. This is the thing. So spec is very much needed for anything. Okay, so this is the gear type, and this is the restive load and the data acquisition system. So here we have the this under healthy gear and fault gear under no load, and if you see here healthy gear and the fault notch tooth gear under load condition. So usually under the load alone, it will be the side bands will be shooting up. Okay, so that is about the study of the signature analysis of the gear. So next comes the method of fault diagnosis in the transformers. So basically distribution transformer is here. I had taken up. So what are the methods for fault diagnosis? Is partial discharge, dissolved gas in oil, and so what is frequency response analysis? So the partial discharges applied to find the location whereas partial discharge occurs by means of acoustic sensors, and it is crucial to configure the sensor and eliminate ambient noise. So dissolved gas in oil analysis. Here we have the different transformer will be filled with oil for cooling purpose, but depending on the temperature, it will be liberating different gases. That gas sensors will be used to find what level of fault it is. That is the analysis. The analysis the percentage of ingredient gases in insulating oil and provide the relation between the obtained data and status of the distribution for transformer. So not suitable for detecting precise electrical or mechanical faults because it is an indirect method. Next is the frequency response analysis. It generates magnitude and phase responses in frequency domain with measured input and output, voltage or current signals, and compared with reference responses of identically constructed transformers and interface comparison. So I had done this in a high-tech transformers. One of our college student of CEG, he was owning this company, and he gave us permission to Mr. Saravanan Balamurugan. Now he's owning his own company, Minatral. You can see that in the website. Is designing the substation, monitoring, and design. It's doing this business good. Okay, so next is the different nearly 10 transformers we got. We named it. We took the specific data, and first we opened it. Before opening the transformer, I had done the sweep test, and after opening also, we'll see what are how the transformer looks like. This is how our transformers in the distribution side. Sometimes this high voltage turns. Here we have the low voltage turn will be near the core that has burnt and it has got stuck with the core, and coil movement. So this is the fault. What are the faults that's occurring? I took these photos, different fault. So punctured. So what to do is, so first without the fault and with the fault, after rewinding, we have to take up. So faulty transformer, healthy transformer, OC and SC test. Okay, open circuit and the short circuit test. So what is happening in our thing we had seen. Next is a sweep frequency response analysis. This is the method. Sweep frequency means usually the frequency will vary with respect to time in a signal. That is called as sweep frequency. So this we need an arbitrary waveform generator. Agilent is used to generate input signals of 10 volt peak to peak, sweeping in the range from 10 hertz to 2 megahertz for 1 second with a sampling frequency of 5 megahertz. Now we have the sweep frequency response consists of measuring the frequency response of transformer winding over a wide range of frequencies and comparing the results of these measurements with a reference set. Differences may indicate the damage of the transformer, which can be investigated further using other techniques by any internal examination. So in the literature, we'll be having, we have to say from where we have taken the data also. There's a frequency band of input signal, probable fault. If it is less than 2 kilohertz, core deformation, open circuit, shorter turns, and residual magnetism. 2 kilohertz to 20 kilohertz bulk winding movement relative to each other, clamping structures. 20 kilohertz to 400 kilohertz, we have deformation within the main and tap winding. 400 kilohertz to 2 megahertz, movement of main and tap winding leads axial shifter. So this is the pattern. So with this pattern, and here we have the different magnitudes. When you have less than 2 dB, it is very low. 2 dB to 3.5 dB, it is low, and 3.5 dB to 5, it is high, and greater than 5 dB, it is very high. So this is the thing. So this is the experimental setup. So you have the high voltage coil, low voltage coil. We have this sweep signal generator. First, I gave the input to the high voltage, took the output from the low voltage side. So we had named it different coils, and what are these things we'll see here. So here peak variation, spectral response for 100 kVA bar 22 kilovolt 433 volt. So here it is a step down transformer, TNEB distribution transformer. It's a good or fault transformer. So it is for we are comparing what is for good, what is for bad, and this one is the comparison. Okay, so in the comparison we have more change in the dB. So healthy and the fault. Healthy is blue, fault is red. Okay. So in this case, in the same wise, we are taken the transformer number will be there. So what is the difference in the thing? So faulty one, we have the more magnitude, and that is one type. Here we have the other type. This is the short-term Fourier transform. So for good fault, STFT spectrogram. Okay, so good transformer. I applied nearly 5 megahertz signal for 2 milliseconds. Okay, so this is the signal that we have to capture, and we have to put the thing. So we'll be having different fault. We can see the pattern. By seeing the pattern, we can automatically detect what type of fault it is. So this for good and this for the punctured one. And so we'll see the patterns. So depending on the red bands, we can classify what type of fault it is also. So that is about the transformer fault. Next is the here we are taken up detection of power quality disturbance using time frequency filter methods. So processing of power system events emulated through a prototype transformer module, single phase matrix converter, and state winding fault in a motor using adaptive peak filters. So you'll be having a comb filter. So whatever the frequencies that you want or stop can be done using your filters. It is a notch filter in which the nulls occur at particular frequency and its multiples. It has a multiple side bands and multiple stop bands. Peaks and dips look like a teeth of a comb with very narrow deep notches where signals are alternated. And here we have the adaptive peak filter. Here when the signal is non-stationary, that frequencies varies with respect to time. The peak filter cannot achieve this task. Using a higher order peak filter will not accomplish the goal because of the fundamental frequency is not constant. A filter which actively tracks the changing amplitude, phase, and frequencies needed to track the fundamental from the harmonics. So we use these two type of filters. This is the block diagram of a matrix converter. So this is the experimental setup, and so this is the switches. So number different frequencies you want to run is we can change the frequency, or how to change the frequency of a how to change the speed of a motor. Either we have to go for change in voltage or going to change in the frequency or number of poles. So this is how we'll be changing the speed. Like it's like a cycloconverter. So this is the experimental simulated one. This is the experimental one. We convert 50 to 50 by 3 low frequency. And if you see here for 3 cycles, we'll be getting 1 cycle. These are the notches, switching notches. Okay. So the same frequency will be getting. So if you pass that signal to the adaptive peak filter, it will be giving what is the amplitude, what is the frequency, what is the phase. All these things can be extracted. This is for 50 to 50 hertz. What are the frequencies that come up? What are the harmonic signals? So this is the what is the amplitude. There are number of algorithms, that is least mean square, and then you have the Kalman filters. We have this one, extended Kalman filters, enhanced phase lock loops for doing all this. These are used for our smart grid also. So what to do is how to measure different in a single grid. We have to take for 1 second 30 parameters, 3 phases. What is the active power, reactive power, what is the frequency, phase. So many parameters will be taken up. Okay, so comparison of what is the simulation and the hardware. So what are the other methods? C means we'll take a single phase. This one 50 by 3 signal has been taken, and we are doing it with spectrogram, substrum, approximation, and the detail wavelet. So wherever you have the high frequencies are considered as noise, low frequency is considered as the information. So to emulate, this is one part. about the that is a matrix converter. Now come to a single phase transformer. We have taken up this prototype module, input and output voltage. Different tapping has been taken. With this, we combined, we had extracted the signals. So the algorithm should track the amplitude, the voltage. Okay. So for sag, swell means this you will have a normal voltage. For one part, you will have the magnitude as higher. So that is called swell. This is the sag. So you have for some time, the voltage will go down and come up. That should be tracked. And then we have the transient. Transient is the one whenever there is a small touching in our, because of the wind, rendu wire touch ago. Appo vandu namakku spark varum. So that is going to be the transient. That also can be detected. You have the interrupt. For some time you don't have any input supply. That is the interrupt, and then it will come up. This one is the flickering. So in the flickering, we have the fluorescent lamp. With the starter, we had acquired this signal and we had applied the algorithms. The flickering is a main important concept. So that is about the power quality events from the transformer. Then we had given the same machine fault signal to the ANF. It is classified. It has taken what is the voltage, frequency, and the phase things. It has tracked and given. So that one. So here we have the switch. Now we'll come to the single phase matrix converter. There are two types. This is the drive. Drive means change in frequency. The simulation study of switching fault in SPMC and its effects on the drive. So I was having a single phase matrix converter. There one switch was, there are many switches in which one has gone out and other one. So we are having different pattern. We have the sinusoidal PWM and the square wave PWM. And I had compared which one is going to be the smooth, the speed. There will be some change in the speed of single phase in the single phase induction motor with a single phase matrix converter fed with 50% duty cycle for 50 Hertz to 50/4 Hertz. That is correct switching. And here we have the faulty switching. So we'll see the pattern of this speed, what happens. This is for good and this is for faulty one. So in the same wise, we are taken up for a this one. We had seen this is a faulty one. One switch is not working here. So what is the pattern? Whenever there is a fault, the even harmonics are going to be switching up. So then is the smart monitoring of machine with the diagnosis. So here I had taken up event-driven wireless communication. So this is the motor, this is the transformer. Here it's a supply. This is the current sensor given to a NI DAC cord, USB 6009, that has been given to the PC where MATLAB and LabVIEW are installed to calculate the FFT. So if you want to replace this, we have to go for a DSP processor or a FPGA. And then we are having the Arduino with GSM that will communicate to our mobile. So it will give the alarm. So there is some fault in this machine, go on attend. On the same wise, transformer, current sensor, we have the given with the NI DAC card given to the Arduino. So it is given directly to the Arduino, and the GSM and the mobile node. So we'll see the setup. So this is the node. This is going to be our DAC card. There is the motor. This is the current sensor. We have the transformer, and this is the Arduino board with GSM, and this is the mobile. So whenever there is a fault is there, we can get the. So we had instead of saying the fault, we gave some number for that. And then this is the algorithm for automatic fault detection. So this is the automatic fault identification, virtual instrumentation block diagram simulation, LabVIEW. This is also in your automatic fault detection block diagram. In the LabVIEW, we had done it. National Instruments, they supported me for this, Vishweshwaran sir. And we had a front panel. So whatever the type of fault, it will indicate what type of fault has occurred. Okay, so this full setup is being used in Boeing aeroplanes and electric vehicle fault diagnosis, all these things. It's in real time. It's in real time. In the conclusion, it is detection of faults in machines and power system, identification of fault type using DSP methods, From digital signal processing techniques, the extent of fault and cause of fault can be recognized. And once recognized, the event of fault can be communicated so that the system becomes a support for smart grid. Sir? Is there any doubt, sir? Please.
Sir,
Okay, sir. Please, sir.
Yes, sir.
Suresh Kumar, sir.
Yes, madam. Good afternoon, madam. I am Suresh Kumar, BHL Ranipet.
Yes, sir.
Madam, this presentation was actually very good.
Yes,
You
sir.
have exhaustively covered all the fault conditions of a three-phase system.
Yes, sir.
Very nice. Madam, actually, what you will do for a DC motor?
For a DC motor. DC motor also here we have what to say? We are giving input to DC input to armature as well as the field.
Okay.
There also you'll be having same type of fault will be there.
Actually,
But here we are going for frequency analysis.
Yes.
There we have to go for RMS value, current value, because there we don't have frequency, no, sir.
Okay. Now I'll tell you why I'm asking this question, madam. Our application, one of the applications, we are using a DC based system where we are also experiencing some kind of a partial discharge, or there could be some sparking and arcing during the operation.
Yes,
So
sir.
we wanted to analyze the actual in fact we wanted to detect that, and then to avoid going to that level, and we have to operate it just below that voltage, assuming such conditions, the frequency what you will get in AC system, what madam has told, it is all multiples of 50 hertz, and they are related to your RPM. If it is on a mechanical side, it will be related to RPM. And if it is related to the power side or stator rotor side, it will be related to your multiples of your fundamental frequency, which is 50 hertz. In DC side, it is very difficult. We were thinking that it will be very difficult to find out exactly what could be the frequency you will get when such a partial discharge occurs. So those area, if madam is having any extra document that you can share.
Yes, sir. Now, yes, sir. Sure, it was a very good eye-opening question, sir. What is here is nowadays we go for special electrical machines. There we have permanent magnet brushless DC machines. There you will be we don't have any input. You will not having spark and all, sir. That you can replace it, sir.
Okay. Now our specific application is that it will have a continuous sparking periodically, not a continuous. It's a periodical kind of a sparking behavior you can see.
Yes,
and there also, the question is that in your madam's presentation is that most of things on a low frequency side, which is multiples of 50 hertz, then you have analyzed using an Arduino board or a kind of a lab component.
Yes,
in
sir.
DC side, the frequency could be on a very high level, ultra high frequency or a very high frequency.
Yes,
in that case, if you want to do that with using DSP, we don't know whether we will be having such a high power or a fast processing DSPs which can handle such a huge frequencies. So we don't know. We were actually I'm also looking for such applications in our domain where we can use, but I don't think it will be available. But maybe if madam is having some data,
I'll visit, sir. Once I'll visit and see your problem, and anything that I can do it, I'll do it for you, sir.
Madam.
Sure.
That's it, madam. That's all. But you have fantastically covered all the aspects of your. In fact, this is now the being offered by our actually, BHL is into this power business. We are also having certain requirement. That means we have solutions also in place where the equipment has to be continuously monitored from a remote location, as well as it is not that failure we have to detect. We have to detect it before it failing. So that is the importance of such a system. So your presentation is very apt and is very current, madam.
Yes, sir.
Thank you, ma'am. Thank you.
Thank you so much, sir. Yes, sir. Sir, any more discussion, sir?
Madam, thank you very much. I think our viewers are not having any doubt, or they are new to the subject, and as our additional general manager, Mr. Suresh Kumar told,
Yes, sir.
it is very apt to the current scenario, and the application and the topic coverage was extensive for those who are in this field. So it's really a very good opportunity for us from Ranipet Local Center of Institution of Engineers to have you as a faculty today, and you have made it to very useful session today. And I take the opportunity to thank you also, madam. Actually, the condition monitoring, right from very basics, you have started from the you have compared the body health with the rise in temperature is a phenomena where you are crossing your normal situation. Like a fever is there means it is having some sort of abnormality. Like that, you have compared to a machine, and you have explained in very easy language to understand people like us.
Yes, sir.
So I am really thankful to you, madam. Thank you very much.
Thank you so much, sir. Thank you one and all for your time and for listening to me. Thank you, sir.
Thank you, madam. Thank you.
Thank you, sir.
Thank you, madam. Thank you.
Thank you, sir.
Rati, madam. Good. Exact 1 hour correct முடிச்சிட்டோம் sir.